Okay. So last class, when we started off, we talked about the thermal chapter. We talked about temperature. We talked about ideal gases. We showed a bunch of proof, and then we went off to the thermodynamics chapter. Okay, and when talking about thermodynamics, we covered a bunch of things. We talked about internal energy. We talked about how internal energy is related to just the temperature, and if we have to break it down, we can break it down into basically kinetic energy and potential energy, right? And when working with potential energy, there is no potential energy, right? When working with ideal gases, there's no ideal gases have no PE. And hence the formula that internal energy of any substance, or let's say gases, the fact that it comprises of Ke and potential energy is no longer valid because there's zero potential energy according to our assumption. So we say that internal energy of any ideal gas can be explained by simply its kinetic energy, right? And hence we say the internal energy of any object, any gas, sorry, is proportional to its K, and hence we know K is given by what? 3 by 2 kT. And if that's the case, I know K is proportional to temperature. Hence, we come to the conclusion that my internal energy is just related to my temperature, right? Fair enough. Now, if that's an idea we are very clear upon, we'll move on to some simpler things that you already know by AS. And also, since we worked with this formula, these graphs last class, you guys have an idea of how to tackle certain questions in thermodynamics when you have to work with the PV is equals to nRT equation and changes of temperature, pressure, and volume. So you guys
Sir,
know how to work
quick.
with these. Yeah,
Sir, I
yeah,
wanted to ask, do we need to remember the AS level content in detail for A2?
no. So you
Because I see
AS.
like sometimes the K equals to Fx, I mean K equals to F by X, those sort of things sometimes need to
Yeah,
be.
those you will have to remember, but not everything. K is equals to Fx. The reason that comes because it's related to oscillation. I'm pretty sure you saw a question related to oscillation. That's why that came into
Uh,
the question. So in oscillation, it again, we have a conversation about K is equals to Fx as restoring force. I'll show that to you. Although most people don't really teach that extensively, but yeah, that's where you will see that those equations. And otherwise, physical quantity from your AS chapter, that it's better to know. So like dimension analysis, units, all those you would need to know. Otherwise, for example, the different chapters, like you guys learned about superposition, all that. No, you guys don't have those in A2. So very different topics, they won't come. But some things that are similar, for example, this, you guys learned this in AS, right? That work done
yeah,
can be expressed as pressure times volume. Yeah. So,
yeah.
some of these things which have been taught to you in AS, it will somewhat be talked about in A2. So you get the idea, okay, this from AS will probably be repeated and I need to understand this. But I will cover that in A2 itself. So there's nothing to worry about there. Right? And the chapter right after this is oscillation. Got
All
it?
right. Yes.
Yeah. So extensively, you don't have to study anything from AS physics. No. Okay. So thermodynamics, we understand quite a few things. Uh, and the main part that is solving the question, what you need to understand to solve question, I've already shared it with you guys. Okay. Now, the thing I want to repeat a bit more, just to cover all grounds, in case you guys have any confusion, is the, work done is equals to pressure times volume formula. This is something you do cover in AS, but I would still repeat it a bit. Now, let's say if you have a container, and this is the most common example whenever working with pressure and volume because it's easy to work with it. Why do I say it's easy to work with it? Because change in volume becomes really easy. When you have this system where you have a piston and container, right? what happens is you have a certain volume here, and by reducing the volume, it is very easy to increase the pressure, right? You can also have a heat supply over here, right? So you can have a thermal exchange or heat exchange, right? So look, with this system, to work with pressure, volume, and temperature becomes really easy. So it's one example that you will see again and again and again. Okay, one of the more common setup. Now, if this container that I have, let's say, and I have the gas working on the surrounding, and I'll explain what that really means. Whoop, what just happened? Okay, so let's say I have the gas working on the surrounding. I'm not doing work done on the gas. The gas does work done on surrounding. What does that mean? That means the gas inside which you have, what is it doing? It is simply pushing on the piston such that it is doing something called work done on the surrounding. So what happened in this process? What happened in this process? The volume del V increased, right? So whenever the gas does work on the surrounding, that is, it applies a pressure and expands, that is, moves the piston outwards, the gas is doing work done on the surrounding. And in this process, what happens? The volume increases, right? And this is an example where the gas loses energy because it's doing work done on the surrounding. It's transferring its energy to move the piston, right? So this is an example of energy being lost of the gas, right? Fair enough. So that is also why when you see this example of, this equation, you guys remember this equation, hopefully. If not, as you revise, you'll remember it. This is what? Change in internal energy. And a positive change in internal energy means that work done on gas. So whenever you have a positive in front of the work done value, that means work has been done on the gas. What does that mean? Volume has decreased, or simply the piston was pushed in. So the volume decreased. And that means I transferred energy into the gas, right? That is an example of work being done on the gas. Hence, energy of the gas increases. If energy of the gas increases, that just means internal energy has increased. So I can either supply heat to my system to increase internal energy, or I can do work on the system to increase internal energy. Fair enough. So now, how do what can I express that work done on the gas or by the gas in formula? That can be explained or expressed very simply as pressure times change in volume, right? How would the maths look like if the volume is decreasing, right? If my volume is decreasing, how would the maths look like? I have the volume and I say, well, my volume is decreasing by this much, right? And this is my del V. So I say, let's say there's a 20 meter cube change in volume or decrease in volume. So I say, if this has happened at a constant pressure, right? If it has happened at a constant pressure, what we say, let's say the pressure was 1 atmospheric pressure or something like that. So 1 times 20 meter cube, right? And my work done becomes 20 joules. So whatever the pressure is, it will be given to you, right? Whatever the pressure is, it will be given to you times, and the pressure needs to be constant for this equation. That is the important thing to look out for. Whenever the pressure is constant and the volume changes, only then can you use this equation. So pressure constant, volume changes, and if the volume decreases, work done is positive. So sign is very important. I must tell you guys, sign is very important in your this chapter, especially. Everywhere it's important, but this chapter especially, they will want to know that do you know work is being done or work is done by the gas on the surrounding. So on the gas or by the gas. To understand that, you would have to express your final answer as positive or negative. Whenever you say a work done is negative, that means gas lost energy or gas did work on surrounding. So your sign over here, especially in this chapter, is very important. Similarly, with thermal energy exchange, heat being provided to the system, positive. Heat being extracted from the system, negative. So whenever you're writing your final answer, especially in these cases, that plus sign, the negative sign is very important. Okay, keep that in mind. Plus sign you don't really need to give, but if you just keep it as it is, that means positive. So yeah, the signs are very important. Got
So
it?
negative, so negative means that the gas is doing work.
Yeah. So in case of work done, that is, if I have U plus Q, so U is equals to del U is equals to Q plus work done. Whenever this value, work done, let's say the question gives you minus 20 joules of work has been done in the system. That means the gas expanded or gas lost energy or the volume expanded. Got it? And whenever they give you positive 20, let's say, arbitrary example, that means the volume decreased, that the piston was pushed in. That means work was done on the gas. That is what it means. Got it?
Yes.
Okay.
And then
Great.
when
So this
if we
is, yeah,
place it in this equation, we follow the signs, right?
yeah, we
Plus
follow
minus.
sign always, always. And I'll show you a few examples of how to understand what this system is going through when I show you a few graphs. So just to give you a bit more in detail idea. So hopefully you understand this formula. Okay. And the proof of this probably you covered in AS. I'm not going to cover that right now. Uh, but in general, if you just look at this, it's a very simple idea. Pressure is, force by area, right? And if I make force the subject, then I find force for the work done formula. We know work done is equals to force times distance. Distance, will you know how much distance it covers? Yeah, sure. How much the piston moves. And then what is force expressed by? Force can be expressed by this, which is pressure times area. Do we know area? Yeah, the area of the piston. So whatever area the circular piston has or rectangular piston, whatever the shape may be, whatever the area of the surface is, that is the area. And the pressure, the pressure being exerted on the piston in the container, right? So that pressure will probably be given to you or you have to find out. But basic idea is pressure remains constant. So you know the pressure, you know the area, and I sub this in over here. I have work done is equals to pressure times area times the distance covered. What does this give you? Area times the distance covered? The volume. So this is how the work done is equals to pressure times del V comes into action, right? This is the simple derivation of the formula, right? I told you I won't derive it, but I mean, I just still did because it's very simple. It's not too complicated. You just look at the diagram, look at the derivation, simple idea, nothing too fancy over here. Do you need to know this? If your question is, there's nothing to know really. It's just substitution of formula. Even if they ask, you should be able to do this. Okay, so this is basic. This is the basic idea, right? So whenever the pressure is constant and there's a change in volume, we say some work has been done. Now, if the change is, let's say, negative, that is, volume decreases, that means work done is positive. Okay. And if the change in volume is positive, that is, the gas expands, we say work done is negative, meaning the gas lost energy. Hopefully, that you have pasted in your mind in some manner. And we'll work with that idea very extensively as we look at the graphs. Keep this in mind. Pressure has to be constant. What do we do if pressure is not constant? Well, the thing is, you guys don't do anything because it's not in your syllabus. So when you guys saw the PV diagram, and I have, let's say, this example, this is what, let's say 400 Kelvin, right? This graph shows that PV is constant at every one of the points. Basically, whatever the P is, V is. So P1 times V1 is equals to whatever, let's take this point. So P2, and this is, let's say, V2, P1. So P2 times V2 is equal. Okay. So your pressure and volume product remains constant through the curve. So again, take this point. This is going to be P3. This is going to be V3 is equals to P3 V3. So basically, any point taken on the graph, whatever the pressure is times the volume is constant with another point on the graph, pressure times volume. It is always equal. That constant is always equal. The product is always equal. Okay. All right. So you just have to keep that in mind. And the thing I want to show you guys is, let's say I have a change in volume from V1 to V2. Okay. What am I doing? Volume is expanding, volume is increasing. But does the pressure remain constant in this process? Does the pressure remain constant in this process? No, pressure didn't remain constant. But what is the work done? Can you say over here work done is equals to pressure times del V? I know that del V is simply V2 minus V1, but you don't know the pressure exactly. Pressure doesn't remain constant. You can't just take pressure like an arbitrary value from the point and say, okay, this is the pressure, or this is the pressure, or this is the pressure. No, pressure doesn't remain constant. That's the main idea. Pressure does not remain constant. So can you use this formula? No. How do you do it? You do something called integration. Okay, but is that in your syllabus? No. Basically, the idea is work done will be integration of pressure from V1 to V2 with respect to dV, element dV. So we integrate from V1 to V2. Is this in your syllabus? Again, no. I'm just sharing it with you guys that this is how non-constant pressure is dealt with to find out the work done. Fair? And I'll again go through this as well. In your case, whenever you have to find the work done, pressure will be constant. Now, the first law of thermodynamics is very simple. You guys already saw the equation that internal energy can be only changed for ideal gases by heat supplied or work done on the gas. So first law of thermodynamics basically talks about conservation of energy, right? Energy can be transferred, fair enough, but in a system, whatever amount of energy is provided remains constant. So in a isolated system, whatever energy you have remains constant. Remains constant. Energy won't be created inside. Energy will also not be destroyed inside. Conservation of energy, and energy can be supplied in. Energy can be supplied in, and in that case, sure, the energy of the system increases. But granted, no energy is supplied in, whatever energy is in the system always remains constant, right? So it's basically conservation of energy that we talk about. And that is just in details explained in a formula. Okay, so as heat is put in, work is done, and it changes the internal energy. So basically, whenever you have a system, you provide some heat to the system, the internal energy does what? Increases. Or let's say I am doing work done on the system. I'm decreasing the volume. I'm putting pressure on the gas. Again, internal energy increases, right? But most importantly, the main indication that internal energy increases is temperature. If given to you, temperature doesn't change, internal energy will also not change. And I will show you again those examples. Okay, because this is the most important bit of this entire chapter, understanding the relationship between different variables. If you crack that, you'll be able to solve any question. So first law of thermodynamics say that the increase in internal energy is equal to the energy supplied by heating plus the work done on the system. So this is your first law of thermodynamics. Very important. Okay, and you guys know this already. Now, all that you guys understand, this is what I want to cover with you guys. The same thing I explained it by these two questions last class. So, you guys already remember how we tackled this question. We found the relation between internal energy and temperature, and with that relationship, we did everything else. Okay, same idea over here. Yeah, any question? So now,
Sir,
yeah,
could I
yeah.
take a screenshot of the 16.3 part? Yeah. All right. Yeah.
Okay. So now, this is where I'll show you guys how the first law of thermodynamics can be used to understand changes in heat, changes in work done, and changes in temperature. Boyle's law, I come back to what we talked about first class of thermal physics. Okay. Yeah, first class, whatever we covered, I'm going to talk about that. Notice over here, what was Boyle's law? What was Boyle's law? Boyle's law was simply that pressure is inversely proportional to volume. Granted, my temperature is constant. So PV is equals to nRT. P is equal to nRT divided by volume. Granted, this entire thing is constant, I can say P is proportional to 1 by V. That is the main idea over here. Granted, we understand that. Let's see two case scenarios, two graphs. So I have a graph for, I have a graph, okay. I have a graph for 400 Kelvin. Look at this. And I have a graph for 600 Kelvin. Okay. So this graph again, the pressure times volume is constant through the graph. Okay. Whatever P1 times V1 is equal to P2 times V2 is equals to P3 times V3. Fair enough. Same thing is with this as well. It's just that the pressure times volume constant has changed. And changed how? What will you say? Did it increase or decrease if the temperature has increased? Anyone? The product of PV has increased or decreased for 600 Kelvin? Anyone can unmute and just tell me. What do we think? For this increased temperature, the product of, let's say, P1, V1, P2, V2, whatever this product of P1, V1 is, so what happened to the product? What do we think for 600 Kelvin? So notice temperature has what? Increased. So what happened to the PV constant, product of pressure and volume?
Will it increase?
Yeah. So if temperature increases, the product PV always increases. So whatever my P1 times V1 is over here, this P1 and V1 is more, right? Because it's simple. Look at the values. Is P1 over here greater than this P1? Yes. Yes. Right? Similarly over here, this V1 is greater than this V1. Right? So whenever, and you don't even need to focus on that. Use the formula. If temperature increases, which it has from 400 to 600 Kelvin, the product of PV always increases. Okay? So very simply, again, whatever my P1 is, what keeps happening? Okay. Whatever my P1 is, and let's say it's, I'll take this one. Whatever my P1 is over here, and then you have a pressure VA. Now you have P2 over here and pressure VB. Now for this example, let's take another point and let's say this over here, it has a certain pressure, right? I'll call this P3. And over here, there's a certain pressure. I'll call this P4. So notice one thing, that the product of P1 times VA is exactly equal to product of P2 times VB. For the same graph, the product of pressure and volume is same. But for a different graph, that is in our case an increased temperature, product of pressure and volume, that is P3 times VD, P4 times VC. So over here, although for this same graph, the product is same, but between the different graphs, the products are different. How so? P3 VD and P4 VC both are greater than P1 VA or P2 VB. So the product of pressure and volume for an increased temperature is greater, always greater. And we can use the equation only to understand that. Okay, it's simple. We just use the equation over here and understand. Again, for the same graph, take any point and find the pressure and volume at that point. Whatever the product of pressure and volume is going to be the same throughout all the points. You take the pressure, volume, multiply. Let's say it's 500, and you take the pressure and volume over here, the product will be 500 as well. Again, over here, do the same pressure and volume, it will be 500 as well. So same graph, pressure and volume, product remains the same. Okay. Any confusion on that? Any confusion on that? That's the most important part of this. That pressure and volume for, sorry, product of pressure and volume for the same graph remains constant. Okay. And if temperature increases, PV increases. Now, the thing I want to show you guys is change in volumes. What happens when volumes change? Let's take the transfer between A to V. A to V. What happens over here? Pressure, what happens to pressure? Pressure decreases. Okay, fair enough. And what happens to volume? It is going from VA to VB. So I'm talking about 400 Kelvin graphs. What happens over here? The volume increases. Fair enough. And what do we know about Boyle's law? Temperature is constant. Right? Right? So if temperature is constant, what can you say about internal energy? Tell me. What happens to internal energy if the temperature is constant?
Um,
Yeah.
what'd you say again, sir?
Or what happens to the internal energy? Does
Uh,
it increase or decrease granted temperature is constant? For this in Boyle's law, we're changing the pressure, we're changing the volume, but temperature is constant. What happens to internal energy?
no energy is like being gained, right? So
Right. So internal
so
energy will be same.
yeah, it'll be same.
Exactly. So del U will be zero. There is no change in internal energy. Why? Simple indication is temperature is constant. Whenever you see temperature being constant, you straight up know internal energy did not change. Why? Because internal energy comprises of Ke plus Pe. Okay. And you know potential energy for ideal gases are zero, so you can remove that. So internal energy equals to the kinetic energy of the ideal gas. And kinetic energy is equal to 3 by 2 kT. So if my temperature is constant, will the kinetic energy change? No. And if the kinetic energy doesn't change, will the internal energy change? No. So the basic idea is look at the temperature. Temperature doesn't change. Internal energy does not change.
Sir, in
Yeah.
this graph, we say from A to B, negative work is done
Yes.
on or positive.
No. Negative. Negative work is done on the gas.
But how? Yeah, it also wrote heat is added.
Yeah.
So isn't doesn't that mean we're doing work on the gas?
Those both are separate tasks. So when you're heat transferring means you're supplying heat, and when work is being done, that means change in volume is happening. Work done over here basically talks about what are you doing with the piston? Is the piston moving outward, hence volume expanding, or are you pushing the piston inward? That is a different kind of work done. That means you're doing mechanical work to transfer energy to the system. And the other is transfers heat by a heat supply. So both are
Oh,
separate types of energy transfer. And I'll
yeah.
explain why the heat thing is written over here. So notice if I get back, internal change in internal energy, zero. Nothing happens. Okay. So now A to B, what is happening? My volume is expanding. Volume is expanding. Right? Pressure is decreasing. So now if I write down my first law of thermodynamics, del U is equals to Q plus work done. What do you think about work done? Work done is over here what? Negative, I told you, right? So work done is negative, right? Gas is doing the work. And internal change in internal energy is what?
But sir, if work done is negative, that means, for example, if it's in a container, it's expanding, right?
Yeah,
So
exactly.
won't the volume increase?
Yeah, that is what's happening.
Oh, okay,
Volume is
sorry.
increasing. Yeah. So whenever
Okay.
volume increases, that means work done is negative. Basically, the gas is doing the work. Gas is pushing the wall, right? And expanding it of the piston,
Okay.
right? So the gas is basically, if this was the initial position, gas is pushing the piston away and doing work on the piston. Got it?
Yes.
Great. Now, yeah. So now when you have change in internal energy as zero, what does that mean? Internal energy in this process does not change. So, but work is being done, energy is being removed from the system. How can it be that internal energy doesn't change? Internal energy should be negative or decrease. The change in internal energy should be negative, or basically, internal energy should decrease. But that's not happening. We know temperature is constant. Temperature is constant. It is 400 Kelvin through the process of VA to VB. Temperature is constant. So this is given to us. Internal energy is zero. Change in internal energy is zero. Sorry. So if work done is negative, then heat supplied should be positive. So if I say minus 20 joule worth of energy was taken from the system by work done on the system by gas, then I also have to say 20 joule of energy was supplied to the system through heat transfer. So if the gas did 20 joule worth of work on the system to expand, that also means I provided 20 joules of energy as heat to the system to make sure my internal energy does not change. This is how you find out different variables in the thermodynamic equation. So this is how I concluded that in this entire process of VA to VB, heat must have been added to the system. Why? Because it's an isothermic expansion. Isothermic expansion, learn this word, means the temperature is constant. In an isothermic expansion, if my granted my volume is increasing, work done is negative, heat supplied should be positive. That's it. Okay?
But sir, if heat is applied or removed, there's won't there
Yeah.
be a change in temperature?
Nope, because it is being compensated by the gases doing work on the system. So whatever heat I'm supplying, the particles are taking that energy and doing work on the system, that is pushing the piston.
Oh, right.
So
So
that it
whenever
is,
there's a change in temperature, that means
yeah,
for example, the gas particles, they're not doing equal amount of work done. Is that right?
yeah. So don't relate temperature change directly to the heat supplied. Basically, whenever you have heat transfer, temperature may increase, temperature may also not increase. For example, in this case, heat is being transferred. Does temperature increase? Nope. Why? Because work is being done. So yeah, if I say this is not a piston, this is a box, a solid box. Nothing, volume cannot expand. So work done is what? Zero. And you're telling me I'm providing heat. So, yes, in this case, internal energy will definitely increase. And that means temperature is also definitely increasing. Got it? So, if it's a solid box and it can't expand, so work done is zero. Granted, work done will always be zero in this system. But I'm transferring heat through some sort of heat transfer, right? I'm providing some heat energy. Hence, the internal energy over here increases. That means temperature also increases. Simple. In this case, my heat transfer directly means temperature increases. Okay. Any confusion still?
No.
Okay. Now, this is the case of A to B. What happens C to D? C to D, my volume is decreasing. Okay. VC to VD. Volume is what? Decreasing. In this case, I rewrite my equation. So work done is what? Positive. But again, this is an isothermal compression. Oh, wrong, 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 wrong. compression. So this is an isothermic compression. Okay. In this case, I mean, even if you write expansion, it's not exactly wrong. It's just negative expansion. But yeah, better to write it as isothermic compression. You won't have to write it anywhere, I guess. It's just for me explaining to you. So yeah, in isothermic compression, when the volume is decreasing, work is being done on the gas. Got it? Work is done on the gas. That means my work done is positive. But change in internal energy is what? Constant, my friend. Why? Isothermic compression. So temperature is constant. Boyle's law, keeping the temperature constant. So del U is 0. So what is my heat transfer going to be? Oop. What is my heat transfer going to be? Negative. What does that mean? If, if I am pushing the piston inwards, right? I'm doing work to this on the system. I mean, on the gas. Sorry, I'm doing work on the gas. That means for the temperature to be constant, heat needs to be extracted from the system. Heat needs to what? Be extracted from the system because I am transferring my energy to the gas by doing work on the gas, by pushing the piston in, by decreasing the volume. But the temperature shouldn't increase, so that heat needs to exit the system, and that is negative Q, negative heat transfer. Heat escapes the system. So my del Q is, or the Q is negative. Got it? So simple idea. I know the thing is isothermic, internal energy doesn't change, and you give me one more information that work is done on the gas or by the gas. Just based off of that, I can tell you, is heat being added to the system or taken away from the system? Important idea. You need to understand this. Questions probably will come similar to this. Okay. Next one. Another case scenario. Charles' law. What does Charles' law say? It says keeping the pressure constant, volume is proportional to temperature. Can we prove this? Yeah, sure. Why not? PV is equals to nRT. I take P to the other side. I say V is nR by P times T. nR by P is constant because pressure is constant. Okay. So V is proportional to temperature. Yeah. V is proportional to temperature. Great, great, great. If V is proportional to temperature, that means if I change the volume, temperature changes. If I increase the volume, temperature increases. Got it? This is the proportion. Keep this in mind. Now let's take a look at the same two graphs. I have a 400 Kelvin graph and I have a 600 Kelvin graph. Okay. 600 Kelvin graph, 400 Kelvin graph, same as before. And what are we going to do? We're going to change the volume, keeping the pressure constant. We're going to keep the pressure constant. Look at the red graph. Don't look at the green one right now. I'm going to look at the red one right now. I'm going to explain the red shaded area first. Okay. By the way, can we use work done is equals to P times del V over here? Yes or no? Simple yes or no. You can write yes or tell me yes. Either one. Can I use work done is equals to pressure times change in volume to find the work done over here? That is work done on the gas or by the gas. Can I use this formula? Think about it. So this work done, can I find this using this formula? That pressure times del V. Yes or no?
Yes.
Yes. Why? Because the pressure is constant. Okay. So
Yeah.
point is, if my pressure is indeed constant, you can always use this equation. Simple idea. So now look. Look at the red shaded area. I go from VA to
Sir,
VB. Yeah.
I'm not really understanding this. He is added, he is removed part. Like, is that a different scenario or?
Which one? Are you talking about the Boyle's law one or new one, Charles' law?
Yeah, like in both. Like, what's it trying to say? Like, what do we mean by this?
So did you understand when I said, for example, A to B, when work is done by
Yeah,
the gas, right? Volume is expanding. So the
yeah,
piston is pushed out, right? So hence my work done in this case would be negative,
yeah.
but my change in internal energy is zero. So don't you think I need to add heat to the system to make sure my internal energy remains constant?
Oh,
That is
okay, okay.
zero.
Yes.
So I'm supplying heat in this case to keep the internal energy constant. So basically, let's say I light a fire in near the container and heat the system up, and I'm transferring heat. Simple. Just if you want to understand what's physically happening, that's what's happening. Since I want my internal energy to be constant or change in internal energy to be zero, and work done is happening over here, that is, gas is expanding, losing energy, but I don't want the particles to lose energy. I want the internal energy to remain constant. So where does the lost energy come from? I provide heat. That is one case scenario, right? The other case scenario that you may be confused of is what is happening C to D. What happens in this case? What happens when I push the piston in?
Work
Work
is
done is
done on the
positive.
gas, which is positive, and
Yeah,
so it's
yeah.
all right.
Exactly. So now, since the particles have more energy, I want heat to be transferred from the system to outside. So I take the heat out. Now, do you know how we take heat out of the system?
No.
It's just, either you create a temperature gradient, so heat is emitted from the system. So, heat is going to exit in that case. So I basically make the surrounding really cold, right? It's this region is very cold. So now the system will be like, okay, there's a temperature gradient. This is really warm and this is cold. So the particles lose energy outwards, lost heat to the surrounding. Or there may be another mechanical system where they're transferring the heat away. Okay, so basically, since I want the temperature to be constant or internal energy to be constant, what do I do? Since work is being done on the system, that is, energy is increasing in the system, I need to remove that energy. How? By heat emitting from the system, by Q being negative. Got it?
Yes.
Great. Same idea we carry on with a different scenario where pressure is constant. So over here, what happens is pressure is constant. I take pressure P1 and I expand the volume. Pressure remains constant. Pressure remains constant in the system,
All right,
but I
sir.
yeah
I
yeah
wanted to ask, like, when we're doing work on something,
yeah
let's say I'm doing work on an object, so the
yeah
object is gaining energy.
yeah.
So is the object doing positive or negative work? If it's gaining energy, isn't it doing negative work?
So we talk about the transfer being negative or positive. So if I am transferring energy to the object, I'm doing positive work on the object,
Yeah.
and the object is doing negative work on me because taking energy from me. So in with respect to the transfer of energy, we say negative or positive. It's always respective, with respect to what? Negative with respect to what? Positive with respect to what? So with respect to me transferring my energy, I am doing positive work on the system. So I'm transferring my energy and increasing the energy of the system. So if I am pushing the piston in, increasing the energy of the system inside or the gas inside, I am doing positive work on the gas. I keep saying system, but gas is more appropriate. So I'm doing
Right.
positive work on the gas, and the gas is doing negative work on me. So with respect to what? It's about how you structure that sentence and say the statement.
All right.
So
So
in
in
this,
this formula,
yeah,
the work done,
yeah,
is it on gas or by gas?
on the gas. In this formula, on the gas. Always. That's why you see positive over here always. They write it as, so when you define, very important what you have asked, when you define, you always say the W over here, they don't write WD. The W over here is work done on the gas. Okay.
Uh, yeah.
That's why you see the positive sign. So whenever the work done is negative, you have to now say, okay, if the formula is del U positive Q plus uh, work done. Now, when I plug in the value, let's say negative work has been done, so volume expanded. Then how do you write it? You will write it as Q plus minus 20. So when you open the brackets, now the formula becomes Q minus 20. Got it? So the formula itself over here in front of the work done, there's a positive sign because the formula states W over here means work done on the system, which is why there's a positive sign. Got it?
Yes.
Great. Okay. So now coming back to the same place, when I have the pressure being constant, actually I need that graph. Yeah. So when I have the pressure being constant and the volume being expanded, so from here, let's say a V1 to a V2, right? So over here, do you see the del V? Del V is V2 minus V1, which is del V. Okay. So what was the change in volume? Oops. The change in volume was this much. Notice this is the change in volume inside the system. So this is the change in volume. So what is happening? Let's write down in terms of the equation we know. First law of thermodynamics. Del U is equals to Q plus work done. Is work being done on the gas or by the gas? On the gas means positive, by the gas means negative. So over here, gas is expanding. Volume is expanding. That means gas is doing the work. So gas is losing energy. So on the gas, the work done is negative because gas is doing the work. So it over here, work done is negative. Now, my question to you is, when volume is increasing, what happens to temperature? If pressure is constant, temperature must also increase. Granted, pressure is constant. Just formula. With respect to our P v is equals to nRT formula. So if my volume is expanding or increasing, temperature must also increase, granted pressure is constant. So if temperature increases, what does that mean? If temperature increases, what does that mean? Internal energy increases. So the change in, so internal energy, let's say, goes from 40 joules to 100 joules because of the increase in temperature. U goes from 40 joules to 100 joules. So what is the del U? Del U is positive 60 joules. This is a del U, change in internal energy. So what is my change in internal energy? Positive. Fair? Positive. That's very important. So my del U over here is positive. But wait a minute. If my work done is negative and my del U or change in internal energy is positive, how does it make sense? How is the internal energy negative? Oh, sorry. How is the internal energy, change in internal energy positive if the work done is negative on the gas? It's a heat supply. So that basically means for the internal energy to have increased, heat must have been supplied. Got it? So my Q, heat supplied, is indeed positive and way more positive than however much the work done is negative, such that internal energy increases. Okay. So basically the idea is to keep the pressure constant, to keep the pressure constant. Oh, where did I go? To keep the pressure constant, heat was being supplied to the system. So over here, when the gas was expanding, right? Over here, heat was constantly being provided to the system to keep the pressure constant. Otherwise, pressure would have decreased. Because expand any system with same amount of moles inside. So I have 1 mole of gas inside. If I keep increasing the volume of the box, the pressure inside the box will decrease because volume is increasing. However, to keep the pressure constant, I have to keep supplying heat to the system, right? That's how the pressure remains constant. So heat indeed is being supplied, my friend. If heat is being supplied, and I know my internal energy, you know, has to be positive. So basically, the heat energy supplied compensates for the negative work done and causes a positive change in internal energy. So this is what's happening from VA to VB. Heat supplied causes the internal energy to increase. How did we figure it out? I simply looked at what happens with temperature. That is my indication to what's happening to internal energy. I saw the temperature increasing. I know internal energy has to increase. If internal energy has to increase and my work done is negative, then the only way the equation makes sense is if heat is supplied to the system. So if heat is supplied, only then will the internal energy increase. Got it? Got it? Great. So basically, I found out heat is being supplied in this case. And these are questions that will come in your paper as well, as you saw last class when we were talking about the graphs. Now, similarly, VC to VD, what happens? My work done is positive, right? And I'm going to a lower temperature, 400 Kelvin. So internal energy must decrease. But wait, if my work done is positive, internal energy is negative, how does that make sense? That means that means the heat supplied should be negative. So heat must have been taken away from the system such that my change in internal energy is negative, such that the temperature decreases. So if I give you numbers, for example, if I was this piston, for example, and I was changing the volume and I decreased the volume such that I did around 30 joules of work, let's say, right? So I did 30 joules of positive work on the gas. And my change in internal energy, I found out, oops, I don't know what that is. So I found out that the change in internal energy is going to be going from 600 Kelvin to 400 Kelvin, negative, let's say negative 30 joules. Because I know the change in temperature. I know the change in temperature. So I know how much energy has been decreased. Why? We went from a 600 Kelvin temperature to a 400 Kelvin temperature. Got it? And how would you find it out? I would ask you guys. How would you find it out? How would you find out the change in energy of the system or the change in internal energy of the system? U simply comprises of kinetic energy. So if you find out the kinetic energy, this is a problem that can come your way as well. So if you find out the kinetic energy of the system at 600 Kelvin, that is 3 by 2 K times 600. This will be the initial kinetic energy, Ke1, then Ke2, which is 3 by 2 K times 400 Kelvin. Whatever the difference between K1 minus K2 is, whatever this is a change in internal energy, my friend. This is what? Change in internal energy. So you know the change in internal energy, and you know the work done on the system. So what should Q be? Q should be Q should be minus 60 joules, because minus 60 plus 30 joules is minus 30, which is the change in internal energy. See if it makes sense. So basically, what I'm doing is I'm using the relation between volume and temperature to understand, is my internal energy increasing or decreasing? If I find out it's decreasing, great. I know work done is positive and internal energy is decreasing. Hence, heat supplied will be negative. That means heat is not supplied but taken away from the system, which is negative 60 joules. So with the numbers, probably it may make a bit more sense. Okay. Heat being taken out of the system. That's what we understood from all of this relation. Okay, so isobaric expansion is what it's called when at the same pressure, volume expands. Isobaric expansion. Temperature increases in such a case. Temperature increases in such a case because whoop, whoop, look at this. Volume increases, temperature increases. That's it. Now, in such case, work done is negative because volume is expanding. So work done is negative on the gas. Great. Hence, heat needs to be supplied to compensate for the negative work done such that my internal energy ultimately increases. So heat supplied compensates for the work done and increases the internal energy. Great. What happens in case of isobaric compression? Temperature decreases. Why? Volume decreases, temperature decreases. V decreases, hence temperature decreases. Okay? Temperature decreases means U decreases, internal energy decreases. But work is done in the system. Work done is positive. So how do we compensate for the positive work done? We take heat away from the system or negative Q. Heat extracted from the system, hence heat is extracted from the system. Hence that compensates for my negative change in internal energy. Got it?
Yes.
Yeah, great. So granted that's clear. Last thing, and we'll finish on time with this topic. Anything else? No. Over here, what happens in terms of PA to PB? So these are again, let's say 400 Kelvin and 600 Kelvin. So over here, pressure law says that keep the volume constant and change the pressure to see the change in temperature. Okay. So if I keep the pressure constant, sorry, if I keep the volume constant, my bad. If I keep the volume constant at let's say V1, what happens? My pressure is increasing, but is anything happening to work done? Let's say for this expansion, PA2 for PA to PB. What's happening? The volume remains constant. Hence, work done 0. So, my change in internal energy in both cases, PA to PB or PC to PD, doesn't matter. In both cases, my change in internal energy is only equal to heat supplied. Because work is not being done. Volume is not changing. Over here, volume does not change. Volume does not change. Only pressure changes. Okay. So over here, if I'm going from PA to PB, is temperature increasing? Yes. It goes from 400 Kelvin to 600 Kelvin. Temperature is increasing. Temperature increases, that means change in internal energy, positive. Because increasing temperature means internal energy increases. Hence, the change is positive. So if my internal energy change is increasing, right, it's positive. Internal energy change is positive. What is Q? Also positive. So to go from PA to PB, heat has been supplied to the system. Okay. So isocoric heating, not expansion. Notice how expansion is not written over here. It's called isocoric heating. Okay. Because the volume doesn't change. So no expansion involved. Yeah.
Sir, uh, when we say the temperature decrease, we're saying that we're removing heat, right?
Yeah. Yeah.
And before this, when we were removing heat, but the temperature was constant, we called that what?
Temperature isothermic expansion or compression, depending on what you're doing. So if you're adding the heat, that means isothermic expansion is taking place. If you're removing the heat, isothermal compression is taking place. Okay.
Yes. Okay.
Yeah. So other one was isobaric, where constant pressure was there. So in isobaric expansion, when I'm adding the heat, that means volume is expanding. When in isobaric compression, what happens? I remove the heat. So the system compresses. Okay, isobaric compression, heat is removed. Isobaric expansion, heat is added. Got it? So these are the small notes you can take to keep it in mind later on. So yes, what happens in terms of again pressure law, that if I go from a higher temperature to a lower temperature at a constant volume, so I'm decreasing the pressure, right? I'm decreasing the temperature or I'm decreasing the pressure, hence the opposite is happening. So in this case, again, temperature is decreasing. PC to PD, temperature is decreasing. Hence, change in internal energy is negative. So Q should be what? Negative. Because there's no work done. It's zero. So the heat is extracted from the system, right? Heat is extracted from the system, taken away. So that is what's happening in isocoric cooling, heat removed. Got it, guys? Clear?
Yes.
Great. So this is done. Uh, yeah, I've discussed the questions with you guys. Practice the questions from thermodynamics. They can throw a few curveballs, but you know the most important parts. That is the internal energy and temperature relation and PV zero state energy relation. And granted you're used to the graphs, anything you can solve. No worries. Now, again, this is a bit of a long chapter, mostly because I have added a lot of derivation, which if you know, great. You'll be able to solve pretty much anything that comes your way in oscillation. Is there any prior knowledge that you need to study this? Yeah. The first chapter that I taught you guys, circular motion, you need to understand that. So granted you have a good concept of that, or a decent concept of that, you'll be able to understand what I teach in oscillation. So next 1 hour entirely, I'm going to focus on oscillation. Hopefully I can cover 2 sections, 3 sections, and I can give you guys some amount of an intuition of oscillations. What is oscillation in general? Have you seen the pendulum, right? There's a clock. Yeah. Let's say I just stick a pendulum over here, right? And let's say I displace this bob or a pendulum, whatever you want to call this. What happens? And if you try it on your own, you'll see. Okay. What you'll see is the moment I displace this bob from the equilibrium position to over here, this bob will start dancing around. It will go here, there, here, there, there. I can do that forever. But point is, the bob oscillates. And this I can call a periodic motion. So as the bob I displace from equilibrium position, can you tell me why this is the equilibrium position? Why is this the equilibrium position? What does equilibrium mean? Forces are balanced out. What? Forces are balanced out. That is what an equilibrium means. Why is this an equilibrium? Because the tension upwards exactly equals the weight downwards.
Sir, could you kindly go back to that thermodynamics? I had a question about to.
Yeah.
So in the Charles' law,
Yep.
uh, or the graph that I showed, is the like is the U constant?
For which one?
Here for A to B.
No, U is not at all constant. Will change because temperature is changing.
Oh,
So if pressure is constant and you change the volume, PV is equals to nRT.
but doesn't U depend on heat energy? It doesn't depend on temperature, does it?
It just depends on temperature. Just depends on temperature.
Oh, but Q is heat energy, right? It's not temperature.
No, exactly. Q is just heat energy, not the temperature. It denotes how much energy I've transferred,
Oh, all right.
right? So let's say I transfer some heat energy to the system, and basically, rather than the temperature increasing, what happens is all of the particles now push the piston away. Hence, volume increases. So negative work done. So over here, what happened? Whatever heat I transferred into work done. So energy went into the system and out of the system. Does the temperature change in this case? No. So you have to think of temperature and the heat transferred as different entities. Yes, temperature can increase if heat is transferred. Only if, only if that energy doesn't escape the system. So if I have a
All right.
box, I supply some heat, volume doesn't expand. So no work then is being done over here. So if I supply heat, yes, del U will increase.
So that
Got it?
means the thermal energy supplied must be greater than the work done by the
Yeah.
gas.
Or the internal energy to increase. Yes. Perfect.
All right.
Yeah. Anything else from this chapter?
Nope.
Okay. Okay. So what I was saying is, whenever wait, 1 second, please. Okay. So now, sorry for pausing, but whenever, let's say, I have such a system where I have, let's say, the bob oscillating, what the bob oscillating means is it is being displaced by a certain distance. So there's a del x. X basically denotes displacement. Okay, keep that in mind. So del x over here means the displacement. So I displaced the bob by a certain distance. And what happens is the bob starts swinging. And this motion, this swinging, can be called an oscillation. A lot of things around us are oscillation. Okay, let's say the Earth goes around the sun. It's a periodic motion, and I can categorize that as an oscillation. Okay, so whenever you have these system where it's a periodic movement, and there's some sort of, like, subjectively speaking, with not respect to physics, but if I just subjectively, qualitatively explain, yeah, whenever you have a rhythm to anything, whenever there's a rhythm to any activity, there's an oscillation, some sort of an oscillation. When you have, let's say, another system, a common oscillation example, I would say, is this system. This mass, and probably you guys will do it in physics as well, or did it in physics in AS at some point when doing practical. So this, if I displace it downwards with, the spring, then it starts bouncing up and down. What is this? Some sort of a periodic motion. I displaced it and it starts bouncing up and down. Why it happens, the analysis of force, velocity, we'll look into that in details. The point is, this object oscillates. Okay. So all of these systems that you're looking at, it's an oscillation. And the object that oscillates is called an oscillator. Okay, so over here, this mass is the oscillator. Over here, this bob is the oscillator. That is basically what oscillation is in simple words. You can look into multiple examples of oscillation taking place around you or anything, right? It's a very common thing and it's very important. Very important. And you'll see why. In engineering, civil engineering, keeping your building safe, damped oscillation, how to damp the effect of earthquake on buildings. Because the building starts oscillating. It goes swinging back and forth. And how do you make sure my building doesn't crash? Concepts of oscillation, very important topic, especially if you're doing engineering, mechanical, civil, but yeah, even in physics in general. Now, look, oscillation, I can explain it in very simple words as a repeated back and forth movement on either side of an equilibrium position. With respect to the examples that you guys are going to be familiar with, this is a very apt description. So, that this one, where this is the EQ position, where my tension equals what? Weight. Okay? There is no other unbalanced force. Over here, whenever I shift it from the equilibrium position, so any repeated back and forth movement on either side of the equilibrium position is an oscillation. Now, what is the oscillator? The object that oscillates and demonstrates principles of oscillation. In simple word, in simple words, the principle of oscillation basically means a period of what am I saying? A periodical change of any measure. So whenever, let's say, the Earth example I said, the reason I said that was it happens in the period of 24 hours, right? That it spins around about its axis. Now, if it goes around sun, that takes 365 days. So that's about 1 year. And that is another uh, example of oscillation, that it spins around the sun. So that's another example of periodical motion. Fair? So it spins about its axis 24 hours, happens in every 24-hour period. It spins around the sun, happens in every 365 days. All of those ideas, you can say, oh, well, it's an example of oscillation in some sense. Okay. So now, if you just look at the ideas over here, displacement, amplitude, angular frequency, these are the terms you're going to be working with, right? Give me a moment. Now, so when I was talking about, again, yeah, these are the things I'm going to explain over here, displacement, amplitude, and angular frequency. But whenever I was talking about this example, or the spring one where it goes back and forth, these are simple, basic examples of oscillation. Now, when I was talking about, let's say, the Earth going around the sun, what I wanted to, in general, I would have expected a response, but uh, it's okay. When I said this as a periodical motion, right? It's true, it's a period, 365 days, 24 hours, but is this really an oscillation though? Based on this definition, is there any equilibrium position over here?
No.
No. So is this an oscillation?
No.
Exactly. So I was just prompting you guys to say, oh, well, it's a periodical change. But point is, 24 hours, 365 days happens in a period. It's not exactly an oscillation. I can't model this as an oscillation. Okay. So it spins around, takes 24 hours, doesn't matter. It goes around the sun 365 days, doesn't really matter. It happens in periods, but that isn't necessarily the point. Point is, sure, even with this example, when you have the bob moving up and down, there's an equilibrium position. In these examples, when I'm talking about the earth, I'm talking about the earth spinning, No, there's no equilibrium position over there in the conversation. Those are not oscillation. Those are simple periodical changes. Okay. So whenever you have the pendulum example, you have an equilibrium position, you shift it, it oscillates. Yeah, that is an example of oscillation. Whenever you have the spring and the bob moves up and down, yeah, that is an example of oscillation. Got it? Do we see the distinction?
Yes.
Okay, fair enough. So I just tried to explain what oscillation is and oscillator is, and so that we don't get confused between different phenomena, right? Now, what are the properties of an oscillator? Okay. Now, when I'm talking about, an oscillation taking place, the oscillator moving around, basically, there are a few variables we consider when we formulate the speed equation, when we formulate the acceleration equation, and you'll see those in details. There are a few things we measure. What are the things and what are the things we consider? Let me take this away. Now, the first definition you guys need to understand is displacement. I just, in some sense, explained it. So when I move this bob in extensible string, so basically the string doesn't expand or stretch. So when I move this string by, let's say, x distance, this distance that you have moved the bob by is displacement. Okay, this is the displacement of the bob. Now, another simple example, when you have this scenario, which you have worked with at some point, or even if not, fair enough. When the bob moves down from the equilibrium position, if this is the equilibrium position, right? And now this is the position of the bob, this change in distance, del x, is the displacement. Okay? And now when the bob moves up again, right? And this thing shrinks, right? So it went from this equilibrium position to this. This is the displacement. Got it? So whenever there's a change in the position of the oscillator, we always talk with respect to the oscillator, where the bob is the oscillator, where the bob is the oscillator. So whenever the bob is moving through some amount of distance, we're either, let's say, moving the bob or we're stretching the spring over here. Whenever we displace the object, the bob or the oscillator, that displacement we denote as x. Okay, so distance of the oscillator from the equilibrium position at any given time. Okay, so if the bob is over here, the displacement is x1, or if the bob is over here, right, the displacement will be x2. Fair. So as we, whatever the position of the bob is or the oscillator is, we define that position with respect to the equilibrium as the displacement. So whatever the equilibrium is and the new position is, difference is displacement. Simple idea. Second is amplitude. Yeah? Any question?
No.
Okay. So now with the amplitude, you will often see this, that if the displacement is explained as x, the amplitude will be explained as x naught. X naught basically means the maximum displacement. So over here, if I carry on with this pendulum example, what is the x naught over here? If this is, I'm telling you, this is the maximum that the spring gets displayed. So over here, the maximum displacement is this distance, del x over here, and this will be called x naught or a or amplitude of the oscillation. Amplitude over here, you guys must have heard of amplitude when working with sound, when working with other waves, right? So you have to understand that amplitude is not necessarily always related to sound or music. It can be anything. Anything that I can model as an oscillation or a wave. And you'll see how we model this as a wave. And that's very, very interesting.
Is wave also
So
considered oscillation, right?
Yeah, it's an oscillation, indeed. So oscillation of the photons, oscillation of the field, the electric and magnetic field, which is a bit more of a complicated topic when you start looking those as waves. But yeah, those are EM waves and those are oscillations as well. Correct. So now amplitude is basically whenever you have any amount of maximum displacement, we call that amplitude. So whenever over in this example, whenever you're displacing it at the maximum position and displace it over here, release it and it starts swinging. So even at that position, that is the amplitude as well. So at the opposite direction, it reaches a certain height, and that maximum height, that displacement with respect to the x-axis is again the maximum displacement. So the maximum displacement, whenever you have in an oscillation, we call it amplitude. And again, when you see the formula, things will make more sense. So it is maximum displacement of the oscillator from the equilibrium position. Very simple. Now, what is angular frequency? Right. Probably I covered this in the oscillation. Now, angular frequency in essence is the rate of change of angular displacement. So omega, remember from circular motion. Over there, we were talking about how the angle changes with respect to time. And it's the same concept over here as well. So you can talk about del theta by del time, which is omega, or you can say, well, I want to know how long it takes for the bob to complete one entire oscillation. That is 2 pi divided by the time period, time
So
taken for the oscillation.
is
Yeah,
it like the rate of change of angular displacement?
yes,
I can define it as that if I'm asked for
yeah,
an example.
yeah. You can define it as a rate of change of angular displacement with respect to time. Sorry, what's the question? How do you define angular frequency?
Yeah. Why do
Yeah.
we have to write with respect to time? Like,
Oh, so when you say rate of change of angular displacement, is it with respect to the position or type? So, for example, if I give you an idea, how do I? Yeah, actually, when I explain this you will get the idea. This is very interesting, deriving simple harmonic motion. But the general idea is, let's say I have a circle, right, and I have a bob over here. So it experiences a certain omega, right? It is changing its theta. Now, this change of theta, I can say with respect to position as well. So let's say this is this y-axis, this is the x-axis, y, x, and I say I'm expressing the angular displacement with respect to position, let's say. So I'm saying this is the positive axis, positive x-axis, and negative x-axis. So I say, well, when the angular frequency I can explain with respect to the position. So basically, how long it takes for an entire oscillation. So 2 pi,
all right.
how far it covers on the x-axis. So I can say for it going 2 pi radians, it goes once over here. That is, let's say this is minus 10 centimeter and this is 10 centimeter. So it covers 20 centimeters once, and that is to reach this point, and again 20 centimeters to reach that point. So 40 centimeters in total. So with respect to displacement, no, not displacement, with respect to distance, you're now explaining the change of theta. Do you get the point? So this
Yeah.
is now you're explaining the change of theta with respect to displacement or distance. Got it? That is
Yeah.
why writing, uh, where is it? With respect to
With
time is
respect to
important.
time.
Yeah.
Yeah.
Got it?
Yes.
Perfect. And I will actually show it to you because you guys have to work with respect to distance as well. The interesting thing is You guys will have to work with respect to distance. You will not just work theta and time. Those are not the only relation. So in circular motion, you work with how theta changes with respect to time. Right now, you will also work with how theta changes with respect to distance. That is going to be very interesting. Now look, we understand what angular frequency is. So wherever they say angular frequency, that is always with respect to time. Okay. Although you will see graph of theta versus distance graph, right? And you will also see the typical theta versus time graph. Okay. But anyways, you won't understand what these mean unless I show it to you. So don't worry. Now the frequency, what is the frequency? How long, sorry, how many oscillations can be done per unit time? So in 1 second, how many oscillations can I do? If I have a circle over here, I have a bob over there, right? And the bob goes around 3 times every 1 second. So that is 3 hertz. Completes 3 oscillation in 3 seconds. Sorry, 1 second. So it is 3 hertz. So although this is exactly how we prove simple harmonic motion, but that's a circular motion topic. And again, when I was talking about Earth going around, and you don't really have a restoring force in those cases, and in those cases it's a periodical motion. There is no equilibrium position, so you can't exactly say that's an oscillation. But the interesting thing is you can model circular motion to oscillations, and I'll show that to you guys how we prove the graphs over here. So we work, in some essence, we work with circular motion to prove simple harmonic motion. Okay, so it has not much to do with circular motion in essence. It has more to do with the nature of oscillation, right? How a particle oscillates and how the distance changes. And when you follow that, you will see, okay, it relates to how particles move in a circle as well, right? So even though, yeah, when the orbits are happening, Earths are moving around the sun, that is not an oscillation, but I can actually use the concepts of circular motion to understand the shape of the graph of simple harmonic motion. And I'll show, if that doesn't make sense to you, perfect. If that doesn't make sense to you, perfect. No worries. As I gradually go towards the graphs, it will make sense. So now the frequency is basically how many times, if I take this example, how many times the bob will go back and forth in 1 second. So when is one oscillation complete? So if I displace it over here, right? And you need to understand this, that when an oscillation gets completed, a few people get confused over here saying, well, it goes from here to here and one oscillation is complete. Nope, that is not one oscillation. Oops, that is not one oscillation, my friend.
So, sir, I wanted to ask, like in circular motion, we learned angular velocity is the rate of change in angular displacement as well, right? So that one is with respect to velocity.
No, that is the same thing.
It's with respect to time, or
Yeah. So angular velocity, it's basically saying how basically the rate of change of the displacement. It's the same thing over here. Rate of change of the angular displacement is same, exact same thing. Why is it called angular frequency over here? Basically, can I say, well, omega is 2 pi by t? Are you clear on this? This part you
Yeah.
understand, right? So
Yeah.
can I say 1 by t is frequency? Do you know this formula?
Yeah.
Yeah, so I basically substitute 1 by t as f. So now they were like, okay, I can model this as angular frequency. So I can model as I can call this angular frequency. So they call this angular frequency. It's the same thing, angular velocity. Yes, you're right, angular velocity. Same thing. It's just we're talking about frequency over here. Okay. So the reason we talk about frequency is in circular motion, you're modeling a particle's velocity, tension, all of those things to understand with respect to position, how tension changes, how, the velocity of the particle changes. We talked about horizontal circular motion, vertical circular motion. So we were working with velocity, forces on the particle, and we were analyzing those stuff. When we're working with oscillation, frequency is a very important part of this topic. So how many times the object vibrates? An earthquake hits, right? The building is vibrating. So what is that frequency of that vibration of the building? How many times does the building go back and forth in 1 second? That frequency is important. So we say angular frequency over here. Okay. How frequently the angle changes with respect to time. That is another way to explain what angular frequency is. It's the same thing. You're right. It's the same thing, but it's just the way they explain it, right? This is basically why. Now, when I was talking about this frequency, basically, what is frequency? Or how do I explain one oscillation? It goes to this extreme position, that is the maximum displacement on the other side of the equilibrium, and comes back to the maximum displacement on this side of the equilibrium. Now, this is one oscillation. Some people get confused and say, okay, the time it takes to cover just this much position, that is from here to here, that is the time period of one oscillation. No, the time period of one oscillation will be from the point displaced to going to the maxima in the other direction to coming back to the maxima in the same position. This is one oscillation. Going forward, coming back. Clear? This is one oscillation. So how many times does this bob do that per second? Per second, how many times does this do that? Okay, that is going to be frequency. Fair? So frequency is 1 by time period. How long for one oscillation is time period. So in 1 second, how many of those oscillations will take place? So if one oscillation takes 0.2 seconds, so in 1 second, how many will take place? 5. 1 by 0.2 is 5. Fair? What is time period? I explained. How will you find it? Simple. Make time period the subject. 2 pi by omega. Fair?
Yes.
Now, phase difference. Have you heard of this? Probably not. Actually, you have superposition and all those topics. You guys must have heard of phase difference. So now, it's the same idea. Exactly same idea, actually. But you guys work with sound and other ways. Probably not other ways, mainly sound. And whatever the concept you have of phase difference over there, same thing over here as well. But with respect to oscillation. Now, if I could show you the graph right now, but you guys probably will get confused when you see the graph. What does the graph even mean? Which is why I want to show you guys the derivation first. But main idea is, let's again, I keep coming back to my pendulum example, because that's the best example I have. I wish someone could automate this for me, but anyways. So I'll position this. And this. So now look. For the first 2 seconds, I will show you the motion. What happens in these cases. So time starts, I start the time. Time starts and I start oscillating. 1 oscillation, 2 oscillation, 3 oscillation. Okay. So for this object, that is the motion of the bob. For this object, 1 oscillation, 2 oscillation, 3 oscillation. What was the difference in these two cases? Both completed 3 oscillation in 2 seconds. But what was different? What was different about these two oscillations? The difference was they were out of phase. The difference was they were out of phase. What does that mean? That basically means that as the object in the first second, so the first second, as this bob moves to this position, that is rightwards, you know what this object does in the first second as well? It moves, but leftwards. Got it? So one moves right, one moves left. Now, in the second second, what happens? The bob on the right-hand side moves back to its initial position rightwards. And the bob on the left-hand side moves to its initial position leftwards. So one moved right, one moved left in the second second. Right? So let's say if one oscillation is taking place, or 3, and it took 2 seconds for each to complete the oscillation, this is what's happening. One goes in one direction, the other goes in the other direction. What do you think is the phase difference over here? What do you think is the phase difference? Any idea? They're completely out of phase. Yeah.
Which
2 pi.
one?
One answer I heard, 2 pi, the other.
How far these two are? The
No,
red ones.
what is the phase difference between these two? So they're displaced by the same amount.
Yeah.
So, but one is displaced left, one is displaced right. So one is displaced right, the other is displaced left. And I release it and they start oscillating.
I think pi. No?
Pi. Okay. So answer is pi. Okay. Well, why not 2 pi? 2 pi basically means it's the same position. Okay. So 2 pi basically means that if I have an object over here and if I have a circle over here, there's a bob over here. Oops. And this is 0 degree and it comes back to the same position. It is 2 pi degree. Now over here, at this point, the object moves rightward. Okay. Rightward. And what is the degree over here? Pi. Pi. Okay. And at this position, the degree is 0 or 2 pi. And this object over here, this bob over here, moves in this direction. If I have a clockwise motion, at the pi radian, it wants to move in which direction? Rightwards. And over here, it wants to move leftwards. So they are completely out of phase, right? And they're moving in different directions. That's the point. Okay.
So this
So
is
they're
similar to what we learned about waves.
Yeah, exactly. Whatever you learned about waves is the same thing, because the oscillation surprisingly can be modeled as waves. That is why it works. So that reference that you have from AS of waves, the reason it works beautifully over here is because oscillations can be modeled as wave. You know how the bob changes its position with respect to time? That change in position with respect to time can be modeled as a wave. And we'll see that. Right? So now look, basically, wherever, let's say, it is at the extreme position on the left, and it is at extreme position on the right. So both of those are at amplitude positions, right? Both of those are at amplitude positions. What does amplitude mean? Maximum displacement, but in the opposite direction. So they are moving opposite to each other. So hence they are 180 degrees out of phase. Now let's change the scene a bit. Let's change the scene that bit. Let's say I have the bob over here, right? And it probably will be more difficult for you guys. but I'll give it a shot. Now I same 2 seconds, one oscillation. We'll try to complete. Okay. Do I have more space somewhere? Yeah, I do. Copy. Perfect. Now, tell me what the phase difference is, and I'll do it. I'll complete one oscillation for the pops. So it goes 1, right? So it goes from this position to this in the first 0.5 seconds, right? Now, next 0.5 second, what happens? Let's see. This will go over here, and this will come back to here. So 1 second has passed. Now, next position, it will go over here. It will go over here. Now, that means 1.5 second has passed. Now, again, the bob comes to equilibrium, and this bob comes to the same maxima. So 2 seconds have passed. What is the phase difference? It may be very complicated to understand because probably was hard to keep track of the movement. But if I try to make your life a bit easier, I will model all of these things laid out for you. So just give me some time. I guess if I had it drawn, it would be better. So for each 0.5 second, I'll model it. So basically 2 seconds are taken to complete one oscillation. So in the first 0.5, first 0 second, what happens? This is the position before the oscillation begins. Next, 0.5 seconds. After 0.5 seconds, what happens? The bob comes to this position, and this bob comes to this position. Next, what happens when 1 second has passed? This bob will be at this position. And this bob, after being in this position, in the next 0.5 will come back to here. So 1 second has passed. Now, if 1.5 second has passed, what happens? Let's see. This bob, after being here, comes back to this position. Okay. Now, let's see for this, what happens? It will go to, because it was here, so it will have momentum in this direction, and it moves rightward. Don't get confused. Don't get confused. If you're getting confused, don't worry. Okay. Now, then when 2 seconds are complete, what happens? Take this. Okay, great. So the bob comes back to initial position over here because it reached a maximum. Now it will come back to here. Typical swinging motion of a pendulum. Simple. This is your physics intuition. Okay. Now the bob was moving from here to here. It was moving in this direction. So from this middle ground, it goes to the initial maxima. What can we understand from this? What is the phase difference over here? Is what I'm asking you guys. I'll help you. So you're saying pi radian?
Pi over 2.
Pi over 2. Perfect. Perfect. So over here, if it moves in this direction, it is also moving in this direction, but it is behind by pi by 2 radian. Which one is behind by pi by 2? I mean, technically, you can say with respect to either one. But if I say this bob is pi by 2 radian behind this bob, yeah, that is accurate as well. The other case scenario would be 3 by 2 pi radian negative 3 by 2 radian, 3 pi by 2 radian. That is another way to express it as well. You guys probably did that in AS as well, where you were doing superposition. You probably learned that the same phase difference can be expressed in a positive number and also in a negative number. So you can say pi by 2, a pi by 2 radian, or you can also say 3 pi by 2 radian. It explains the same thing. Okay. So either you can say with respect to what you can say either. So yeah, you're right. So as the bob moves in this direction, this bob is pi by 2 radian behind. It moves over here in the maxima over here. Then this object over here reaches the middle ground. And then as it moves backward, this doesn't move backward. This actually still continues to move in the same direction to reach the maxima. So everything that is happening to this happens 0.5 seconds later to this object. Every position that is taken by my bomb on the left is taken by bomb on the right 0.5 seconds later. And 0.5 by 2, I'm telling you guys, 2 is the time period. What is 0.5 by 2? 1/4. Right? And what is 1/4 of 2 pi? Pi by 2. Got it? See how we can, very neatly find out the phase difference. Right? So we saw how much, let's say, in terms of seconds, one of my pendulum was behind. We saw the right-hand side pendulum was 0.5 seconds behind for every position. So we saw, okay, 0.5 seconds is the difference. Time period is 2. I found 0.5 by 2, and I said 1/4. And 1/4 of 2 pi is pi by 2. So phase difference, which is always with respect to radian, is pi by 2. You're right. 90 degrees. So hopefully you guys understand what phase difference is. Okay. That's the core idea. The reason I'm going slow today is once you guys understand the basics of oscillation, I'll be able to show you the derivations very fast. Okay. Now, point is, phase difference measures how for an oscillation, how much an oscillation is in front or behind another oscillation. Very simple. Okay, it's a measure of how far an oscillation is behind or in front another oscillation. So basically, when you saw the waves, if you look at the waves based on your AS idea, right? You guys are used to this. What is the phase difference over here? What is the phase difference over here? So, well, I'll make it a bit easier, I guess. Okay.
Sorry, sir, I just went
Pi
out of
over
the room.
2.
Did we just start simple harmonic?
No, I'm just still going over the thing I was sharing over here. You know how the pi over 2 you guys said, which was correct. I was just explaining that. So phase. I'm just talking about phase still. And next, simple harmonic motion. Yes, what you said is correct. Pi over 2. So I basically asked, what is the phase difference between these two waves? And you said pi over 2, which is correct. So if I displace the wave again in front by this much, what is the phase difference now?
Pi.
Pi. Okay. So this wave completely cancels out this wave, right? And you guys have studied this. So if superposition takes place over here, that basically means there's no wave, no resultant wave. So yeah, that's how we find out phase difference. How far ahead an oscillation is compared to the other one, right? Or behind, right? There are two ways to explain it, the phase difference. Now, whenever you have a pi rad ahead or behind, it is an antiphase. It is an antiphase. And in AS, you have extensively studied this, right? So whenever things are in antiphase, they can tend to cancel each other out. And their motions are completely opposite to each other all the time, right? Now, when you can also explain this pi radian of phase difference as half a cycle. So you can talk with respect to radians, that is phase, or you can say with respect to a cycle. Remember, I was just explaining to you guys two bobs, and one was pi/2 ahead. So in this case, I can say they're 1/4 a cycle behind or in front of each other. Can I not say that? Yes, I can. So that is another way to explain it. Now, simple harmonic motion. The most important and the exact topic you guys are going to study. This is everything. If you understand this, your life gets easier. Simple harmonic motion is a type of oscillation in which the acceleration of a body is proportional to its displacement but acts in the opposite direction. Wow. Quite the long definition and a lot of important keywords. A lot of important keywords. But if I turn this into a formula, what is it? A type of an oscillation, you saw the examples of oscillation, spring example. So bob moves up and down. Or the pendulum example, the bob moves right or left. Periodical motion and there's a displacement with respect to equilibrium position. One up and down, the other right and left. Now, what is SHM? Simple harmonic motion. What is SHM? So in simple harmonic motion, what really happens is if the body is displaced, let's say over here, I pull it down. What happens now? There is, due to a displacement, due to me stretching the spring, there is now an upward force on the mass. Have you tried this in a lab? Have you seen how you displace the mass? It starts bouncing up and down. So basically the point is, when you displace the mass, there's an upward force due to the elastic energy in the string. Sorry, the spring. So why is this upward force coming? Because you stretch the string and the string wants to contract and reach its equilibrium position. So it's called a restoring force. That force that applies, when you were talking about F is equals to kx today, towards the beginning of the class, this is where it comes in. Where is the restoring force coming from? The spring. So however much you extend the spring, all right? You extend the spring, that is x. And what is k? The spring constant. And that applies the upward force on the mass to move it upwards. And if a force is exerted on the mass, can we say there's an acceleration? Can we say there's an acceleration on the mass? Or the mass is accelerating? Yes, we do. Yeah, perfect. So we understand that when we displace the object, there's an acceleration towards this equilibrium position. So isn't this the equilibrium position over here, if you model it? Yes, it is. So when I extended the spring and I pulled the mass down, now the acceleration is towards which position? Towards its equilibrium position. Towards its equilibrium position. So there's an acceleration towards the equilibrium position. Now, I want to understand something from you guys. Why does it say that the acceleration and the displacement is opposite in direction? Why does it say that? I understand whenever there's a displacement, there will be an acceleration. That much I'm clear. I just explained it to you guys how the acceleration takes place. and stretch the object, extend the spring, and there's an acceleration upwards. Why? Because the spring, there's an elastic force due to the spring, and it pulls the mass upwards. But why? Why is it opposite? Why does it say it's opposite? The reason is, my friend, if this is the equilibrium
Sir,
position,
could you explain this example again? So it's accelerating downwards, right?
no, upwards. So when I extend it, acceleration is upwards. Why? Because you have stretched the string or the spring, and there's a restoring force on the spring. So, you extend the spring, you store elastic energy in the spring, and the spring wants to contract. So the F is equals to Kx formula that you mentioned towards the beginning of class today. This comes into play. So when you extend the object, there's a force upwards on the mass. Why? Because you've extended the spring. So the spring wants to pull up the mass. Okay, got it? And how can we quantify that? The spring constant of this spring times however much displacement you have caused by moving the object. So this x, this displacement times the k is the force with which your mass is being pulled. Got it?
But so how are
Very
they in
good.
the opposite direction?
The displacement and the force.
Yeah.
Yeah, that is what I'm going to explain. Yes. So look, I displace the object downwards. Agreed? I displace the object downwards to over here. And the acceleration is in which direction? When I'm talking with respect to pulling the object down, I pull the object down and now I have an acceleration upwards. Upwards. So isn't the displacement and the direction of acceleration opposite? You tell me. It is. Yeah. So when I displace it down, the string pulls it up. That is why it is opposite. Right? So two things are clear. Number one, you displace object, there is an acceleration. There is an acceleration. Number two, the direction you displace the object in, the acceleration is in the exact opposite direction. So if I pull the object down, the acceleration will be upward. Are we clear on this? Yes?
Yes.
Perfect. So the idea is I move the object from its equilibrium position, I get an acceleration due to something called a restoring force. Over here, what's the restoring force? The force caused by the spring. Okay? By the extension of the spring. You can find that out using F is equals to Kx. What is the force applied upwards? Now look, and I will talk about this in maths term very in details, although I don't need to teach this exactly, but where is it? This. No, not this. This. This is the beautiful explanation of the spring example, how the forces really vary. Okay. And you will see how we use F is equals to Kx. You won't understand anything by looking at it. I need to explain it. But our point is, you can quantify everything and solve the problems when you're working with spring, when you're working with the pendulum. All of these cases you can quantify into formula. Quantify into numbers, and you can express the equations and understand how the acceleration is varying with respect to the position, right? So we will do that later on. when things get a bit more advanced. Not right now. I also have videos online if I don't cover it, because it's not directly mentioned in your syllabus to show the examples in details and derive the equation. It is something that will be tested in the paper. So when you write the papers, they will ask questions with respect to pendulum, with respect to the spring. So then you have to do those things on your own. But I have still explained this in videos, and I'll try to pack it in the class. But if not, you will be able to see the example videos otherwise. Yeah, any question?
No.
Okay,
Do
so
we
now,
have the link to the video?
yeah, I will post it in the classroom. Is that okay?
Okay, yeah.
So those two are example videos. So I derive the equations which helps you solve similar problems in the exam hall. Okay, that's it. And you will see how it makes sense for a pendulum and also it makes sense for a spring. Now, coming back to over here. So what we found out, what did we find out over here? That when I displace, there's an acceleration, and the direction I displace in, acceleration is in the opposite direction. Perfect. Now the question is that are they proportional? It just turns out to be that whenever we have simple harmonic motion, the acceleration and displacement is actually proportional. So when you take these examples, right, the bob, or like this one, or let's say the spring one, whenever you plot the displacement of the bob and the acceleration of the bob on a graph, what do you find? You find that acceleration, the magnitude of acceleration, is exactly proportional to displacement. So what that means is, if I displace the object, right, the mass over here, by this much, acceleration increases in a certain proportion, right? So if, let's say, if x goes from 5 to 10, so it went twice, right? Then the acceleration will go, let's say, from, by the way, this is not equilibrium. This is not equilibrium, let's say. This is not equilibrium, let's say. It's probably one of the position that I have extending the object in. So probably this is the equilibrium position. Okay. So I have displaced from 0 centimeters, which is the equilibrium, to 5, and then to 10. Got it? So what I'm doing is, this is the equilibrium position. Understand this? This is the equilibrium position, and I have extended the spring to a position of 5 centimeters. And now I'm further extending it to x is equals to 10. Got it? So x is equals to 0 to 5 to 10. So how do you think the acceleration will vary over here? So going from 5 to 10, what is the increase in displacement? It went twice. So if the acceleration at x is equals to 5 is, let's say, 2 meter per second square, what will be the acceleration over here in x is equals to 10? Any idea?
4.
Exactly, 4. That is what proportionality means. So they're linearly proportional. Got it? So A, acceleration, is linearly proportional to the displacement, but
But it's
opposite.
to the negative. So
Yeah.
if the displacement is 10, then the acceleration is -4.
Exactly.
So
You
doesn't
can
that
also say the
mean,
opposite thing. You can
so
also say the
doesn't it,
opposite thing. Yeah. If acceleration is +4, displacement is -10. You can also say that. Depends what direction you consider plus and what you consider negative. If you
yeah,
consider up as positive, then your numbers vary accordingly. Yeah.
if
Go ahead.
acceleration is negative, it means it's decelerating.
Yeah, accelerating in the opposite direction. Yes. Decelerating. Yes, you're technically right. Yes.
Why? Yeah.
So what that means is, if I pull the object down and I say, well, I say down is negative as usual, but up is positive. So, or what is the displacement? Displacement is what? Negative in this case, because I'm pulling it down. So x is negative. And what is my acceleration going to be? Or deceleration going to be? -4 at this position. Sorry, +4 at this position, which is upwards. So it is now going to accelerate what? Upwards. Got it? So I displace it down. So negative displacement, and the acceleration will be upward. Now, if I do the same thing at the topmost position, so if I remove all this and say, oh, well, I'm going to basically stretch in the string over here. And what happens in that case is now displacement is positive. Got it? Displacement is positive. And acceleration will be downwards because you're pushing the string in and it wants to expand. So acceleration is downward and is negative. So yes, you can technically say it's decelerating. Not wrong, not wrong. And it's you can say it's decelerating downwards. Sure, technical terms, but it is actually accelerating in the opposite direction. It is decelerating upwards. So the right way to say it is acceleration over here is negative with respect to up being positive. So it is decelerating
So in
upwards.
exam, do we have to state, or will the like
What will you have to state? You will write in
mention?
numbers. You will write what is the acceleration of the object. You will say negative this in this position. -10, -4,
Like
-5,
we have
whatever
to
number.
write whether we're taking upwards, positive, negative.
So the context will be given to you. If there's a graph, well, which I will show you. So yeah, for example, this acceleration versus displacement. If they're giving you such a graph and saying when the displacement is negative and acceleration is positive, so you go by whatever they've given to you, right?
Yeah.
So if they show over here that position one is negative displacement, so they're taking what? Left as negative and sorry, right as negative and left as positive. Got it? So you just go by that logic.
Right.
Mostly you will have to work with graphs, and I will show it to you as I show the graphs, as I derive the formulas, it will start making sense. So point is, I will end it very fast. Sorry to keep you guys waiting, but point is my acceleration and displacement is proportional, but in opposite direction. Fair. And now you guys know that every single time we remove proportionality, we have to include a constant in the equation. So I want to remove this proportionality, and people have found out by experiments that whenever you remove the proportionality, the constant comes out to be omega square. What is omega? So whatever the frequency of the oscillation is, right? Whatever the angular frequency, not frequency, my bad. Whatever the angular frequency is or angular velocity is of the bob, squared is the constant. And you will be like, where does this come from? How do you derive this? I'll show it to you guys, no worries. The revision is not exactly in your syllabus, but I will still show it to you. This is the proof. And I have proven this once on YouTube as well, but I will show it to you guys again. When we do, this much will be asked to you guys. It's good to know the derivation of omega square, how the omega square comes out to be, how we find the omega square, why is it omega square, you will understand. But this is the main thing. This you will have to know. This you will have to know to an extent. Yeah, all of this you have to know. That how displacement varies with time, how velocity varies with time. And from that, we find out how we get the omega square. It's a pretty neat derivation, but I'll show it to you later. First, I'll explain this and then move on to the derivation. Point is, when we remove the proportionality, we get omega square as the constant. That is a constant. Okay. Does the angular frequency change of the bob or angular velocity change of the bob as oscillation takes place? No. The rate of change of theta does not change. Doesn't matter what position it is in. What changes though? The displacement changes, acceleration changes. Got it? And hence velocity changes. These three things change. Nothing else changes. And yeah, in terms of forces change as well. But when I said acceleration changes, that is a given that obviously force will change as well. F is equals to ma. But these three things, acceleration, velocity, displacement. Got it? These three things change. And you can say theta changes as well. And I'll show to you guys how it all makes sense when I explain. But point is, angular frequency doesn't change. Clear? Angular frequency does not change. Now, any confusion till this point? So this is the formula you guys need to remember. Acceleration is related in proportion but oppositely to displacement. And I showed how the acceleration is it comes into action with respect to pendulum or spring. So in pendulum, last thing I want to share, sorry guys. So in the pendulum, can anyone tell me where the restoring force comes from? Where is the force coming from to get back to this position?
Air
Restoring
resistance?
force. No, we consider air, there's no air resistance.
Weight?
Yes. So gravity.
Well,
So let's do this. There's tension over here, and there's mg. There's a theta over here, right? So try to remember your circular motion thing. Mg cos theta. Can I say this as mg sin theta? Yes. So T is equals to mg cos theta. Okay. So point is your there's no unbalanced force in this direction. Is there? No, because my tension is being balanced by mg cos theta. Fair? So there's no unbalanced force in this area. So that is why the bob doesn't move up and down with respect to the string. With respect to like bobs in your, what do you call it? Your clock, your pendulum. But it does move in this direction. Why? There's a restoring force. What is that? Mg sin theta. So you're right, due to gravity. So if I break mg down into two components, one in the direction of the string, the other perpendicular to the string, this is why the bob moves towards the equilibrium. So which direction does this force point towards? Towards the equilibrium. If I draw again, over here, over here, over here. So look, the direction has now changed of mg sin theta. This is also mg sin theta. This is mg, okay? And this is mg cos theta. mg cos theta. Oh, sorry, it's very smoothy over there. The point is, mg sin theta is the component or restoring force, unbalanced force. Are we guys clear on this?
yes.
Perfect. So we understand in case of spring, what is the restoring force? The elastic force, F is equals to kx, and over here it is due to gravity. In the case of pendulum, hopefully you understand how the restoring force works. So now next class I'll show you how we get the graph, how we can model oscillation as a graph. So I told you guys 2 chapters will be done with, and these 2 chapters done. Next class, we start deriving simple harmonic motion. This will be hopefully fun if you guys enjoy derivation. Done. And tomorrow there won't be a class. There will be on Monday. I'll write it in classroom. 2 things I'll write, and there will be a class on Monday, not today. Second thing is what was I saying? Oh, your the videos, the 2 videos of example. I'll link it down. I'll actually link down the entire playlist and specify which are the videos for the example. But yeah, you can look into it. So pretty much done for today. Done for today. Next class, 17.3. We start. Any other question? Anything in mind?
No.
Perfect. So we're done for today. Thank you guys for attending. I'll end it today. No class tomorrow. Class next on Monday, same time. Perfect.
All right.
Great.
Thank you, sir.
No worries. See you guys. Bye bye.